So let's talk about fluid exchange over capillary walls. Okay. What we have here so we have a capillary. This is the arterial end of the capillary, and here's the venous end of the capillary. Can you see here? That's what I'm saying. You see here? All right, I put a V there for venous end. Okay? Now, we can have fluid. So this is your capillary. This is your interstitial area. Okay? Does that make sense? The capillary where blood is in here. Your interstitial area is here. Okay? Now, we could have fluid going from the capillary into the interstitial area. That's called filtration. We could have fluid going from the interstitial tissue back into the bloodstream, and that's called reabsorption. We're reabsorbing it back into the bloodstream. Okay? I'm going to go somewhat fast with this because this should all be reviewed for you guys when you did blood vessels in A&P2. All right, now, just so you can see what's going on here, this is where blood is, or not blood, this is where fluid is in your body, okay? How it's distributed. You have your bloodstream over here, that's the extracellular fluid. It's outside the cells, okay? You also have it in other places, like cerebral spinal fluid, there's fluid there, it's outside cells. You got fluid in your knee joint, that's outside cells. You got fluid in your eyeball, that's outside cells, okay? But we're talking about in the blood here. Then you have, this is your cells, so you have you have fluid inside the cells. We call it intracellular fluid, where most of our fluid is in our body. It's intracellular, about 60%. And then we have some fluid that's going to be outside the cell, so it's still considered extracellular fluid, but it's in between cells. We call it interstitial fluid. Okay? Does that make sense? And what I drew over here, we're talking about fluid that goes here into interstitial fluid and fluid going from the interstitial fluid back here. Okay, does that make sense? We put that together? All right. So we have two forces to get fluid, that gets fluid into the interstitial area and back. We call these Starling's forces. This is a different Starling, Frank Starling's law of the heart. He's a different guy doing this. So this is Starling's forces. We have two forces. Hydrostatic pressure, which is an easy one to understand. Okay, and we'll talk about that. That's the blood pressure itself. And then we also have something called oncotic, and some people call it osmotic pressure. That's a concentration pressure to have fluid go towards that solute, whatever that is. We won't get into that one. So first let's talk about hydrostatic pressure. Hydrostatic pressure is the blood pressure itself. Hydro meaning water, right? It's the blood pressure. So we have blood going into here. There's a momentum, there's a pressure that's happening here. And at the arterial end of the capillary, it's extremely high. The blood pressure coming into here is going to be high, right? But the fluid over here, the hydrostatic pressure that's up here in the interstitial area is very low. There's really not much fluid up here at the arterial end. Fluid didn't get there yet, so there's not much fluid up there. Does that make sense? There's more fluid here, so there's more pressure here. There's less pressure here. So look what's going to happen here. The fluid that's coming here is going to be able to go into that area. Because it's going from a high pressure to a low pressure. And that means we're putting more water up there. And it's going to keep on doing that. But look what's happening as we do this. We're taking the fluid here, not blood, but the plasma, right? We're taking the fluid from here into interstitial tissue. And gradually, this is going to get more pressure up here because of all the fluid that's going up there. Does that make sense? And we're losing pressure down here, hydrostatic pressure. So there's going to be a point someplace in the middle where there's going to be a flip-flop, where the fluid is going to go this way. Because we're building up more fluid up here and less fluid over here, so now the pressure's high here and then low here. But the thing is, think of momentum. The fluid is always going to keep on going that way. It doesn't. The fluid isn't going to stop, so it keeps on going. It'll only equalize when you're dead, right? So it does that wave. Okay, kind of like the ocean. The water comes in, and then it goes back, right? So we have no mechanism to do this. This is just physics. Like the ocean, the water just goes that way and comes back. If I take this pen and I drop it, it's just going to fall because that's the way physics says it. There isn't anything to say, okay, we got to release a hormone to get the fluid out there and another hormone. No, this is just physics. This is just what happens. Okay? Now, it would be nice if, let's say, 30 liters goes out there and 30 liters comes back. But the way the physics is, it doesn't work that way. Okay? If you're in medical school, we would break it up and calculate why that all happens, but I'm going to cut to the chase. It doesn't do that. Instead, 30 liters goes there, but only 27 come back. That leaves 3 liters in the interstitial area. That's not good. Because eventually more of it will go up there, the next round of fluid that goes there. And it'll start building up, building up, building up. So we got to eventually get that fluid back into your bloodstream. So we can do that. We have a system that brings that extra fluid back. What system is that going to do? Or what system are we talking about? What's the system that's going to bring fluid that is in the interstitial area to bring it back into the bloodstream? No. No. Lymphatics. Okay? Lymphatics. So we have lymphatics over here that is going to take that extra 3 liters and brings it back to the bloodstream by a different system, which I'll show you on a picture over here. But the lymphatic system is going to bring, it has 2 jobs really. One end of it is going to bring that fluid back, but it also works like customs does at the airports. In order for you to come back to the country, well, we need to make sure you have no drugs, there's no guns, that you're coming here like that, right? So it acts as a customs. So we have lymphatics over here that before the fluid goes back, it's going to go through lymph nodes, customs, to make sure there's no cancer cells in there, that there's no bacteria, there's no viruses. Because those lymph nodes are loaded with white blood cells. Police. To kill those things. That's why the lymph nodes, if there is something going on, your lymph nodes swell because the white blood cells are, before they send that fluid back, it's going to kill those things in there. And there's a lot of activity going there. So it's a nice setup. So we could, acts like a filter. It cleans out any bacteria, any cancer cells before it becomes something bad. So I look at it as like a custom, the customs are like airports. Right? Does that make sense? So that's hydrostatic pressure. Okay? So it's higher at the arterial ends that I showed you over here. It tends to push the fluid into interstitial area. And then it's lower at the venous ends in the capillary, so then the interstitial fluid can go back this way. Is that clear with that? Review, okay? All right, so this is the picture trying to show you where the lymphatics come in. So here's, the left heart, right heart, right? So you have the left heart here that's going to pump blood. Here's the capillary bed. It's going to have this wave. So 30 liters goes into the interstitial tissue. 27 come back and goes right back to the heart. But there's another 3 liters that sits there. They got to go into the lymphatics, but as it does, there's a bunch of different lymph nodes all around here it has to go through, but eventually that fluid will go back into the veins to bring up the blood, or get the blood back, blood volume back up. You see where lymphatics come in now? And see how the immune system works. Okay. So let's now talk about a different kind of force, a different kind of pressure that happens simultaneously with the hydrostatic pressure. This is the other side of the story. But they happen together. But to make your life easier, let's just isolate it. I isolated just showing you hydrostatic pressure. Now let's talk about something called oncotic pressure. It's also called colloid oncotic pressure, or it's also called colloid osmotic pressure. It's all the same thing. I don't know how it was taught to you and what words were used, but it's the same stuff. Oncotic and osmotic means concentration. Okay, so we're dealing with a concentration gradient, not a pressure gradient. Okay? So what happens here is that we have large proteins that are floating in the bloodstream. They're called albumins, and they're made by the liver. And we have other proteins in there too, fibrinogen, clotting factors and stuff, but albumin are these bigger ones that are going to be the major factors for this oncotic pressure. Now there are certain proteins that are up here, but we don't have that much. But it's important that you know that there's some proteins up there. And we got to deal with concentration. So pay attention with this, and you can always rewind it and with a video and stuff. So, but understand what's going on here. When we deal with oncotic pressure, now at this point here, we're just looking at this area here. Draw another one. So we're just dealing with this part right here. Now, at this early time, how much fluid is up here? A lot, a little, a very little. Okay? Over here, how much fluid is here? A lot or a little? A lot. Okay. Now, which area, and we're just looking at this area here, which area is more concentrated? Here or here? Are we talking about interstitial area or the capillary? Okay. Think of lemonade. Okay? Lemonade is made of water and crystals. Right? Crystal-like crystals? Okay. Now, if I just take crystals and pour them into the pitcher, there's no water there. I touch my tongue on it. Is that going to be very concentrated or is it going to be dilute? Concentrated. Because there's no water there. Does that make sense? So, I ask you, in this area here, is there a lot of water here or little? Little water. Is there a lot of water here or little? A lot. Is this more concentrated or more dilute? More concentrated. Does that make sense? And it's more dilute here. So let me ask you this. In the area there is more concentrated, and so we have a little bit of water here, a lot of water here. Where does the water want to go? Into interstitial area, or does it want to go into the capillary? Does it want to go where there's more concentration or more dilute? Concentration. Water follows solute where it's more concentrated. How do I make that lemonade taste better? If it's so bitter, am I going to add water to it or take water away from it? Add water. So water is going to be drawn where there's more of a concentration. See, hydrostatic pressure was a pushing force. Oncotic pressure is a pulling force. You see that? So what's happening here is, look at this. Very dilute here. There isn't many proteins here, but there isn't any water over here either. But there is some proteins. So this is highly concentrated. It's crystals without water. But this is dilute over here. So what's going to happen here is water is going to be pulled into the interstitial area because of the oncotic pressure. Is that clear? And it'll keep on pulling it there and pulling it there. But now look what's going to happen. We have a lot of water here. Now this is going to be really dilute. And over here we're getting more concentrated because the water's leaving here, right? Does that make sense? So you're going to have a reversal happening here. So the fluid that goes into the interstitial area is because of two reasons that happen at the same time. Hydrostatic pressure and oncotic pressure. Hydrostatic pressure pushes the fluid there, oncotic pressure pulls the fluid there. But it reverses because this becomes dilute, this has more fluid over here, so then it reverses. Hydrostatic pressure will force it this way, oncotic pressure will pull it this way. You see it? Okay? So, to sum up here, if I can draw it this way, you can see it. Hydrostatic pressure in the capillary is going to be very high in the arterial end, but then gradually get low. Does that make sense? And the interstitial area, it's low at the arterial end, but gradually goes high. Because we're putting all that fluid out there, the hydrostatic pressure gets high over there. Oncotic pressure in the capillary is low over here. And gradually it's going to get high. But the oncotic pressure over here is high, it's going to draw the fluid over here, but gradually it gets low. Okay? So it's everything I wrote over, explained to you over here with those things. Again, water follows solute. Water will be pulled where there's a higher concentration of these proteins. Okay? And that's what I just repeated. I just said it to you. Word for word. All right? This is the same thing, just showing a picture form where the fluid goes. Okay? Direction, everything I just explained to you, it's all written here. Okay? And I took all these pictures, all these slides from my A&P2. This is how I usually teach the A&P2 section. Okay? So in summary, at the arterial end of the bed, hydrostatic forces dominate, right? The hydrostatic force, right? The blood pressure itself. And at the venous end, when we deal with the blood, with the capillary, it's going to be high over here, right? And like I said, the lymphatics, see the combination, the 30 liters of fluid that goes out there, and then 27 come back, and it's due to both the hydrostatic pressure and the oncotic pressure does that, but 3 liters stays out there, the lymphatics will take that back. Okay? And this is showing the same thing I kind of drew from you guys. Make sense? I hope, that should be all review for you guys.